Hello everybody, this is Avantik here. Today we'll be discussing about linear model for regression and classification. Agenda is as follows. First of all, we'll understand simple linear regression using ordinary least square method, gradient descent algorithm, the math behind it, regularization techniques like Ridge, Lasso, ElasticNet, logistic regression for classification, online learning method, stochastic gradient descent and passive aggressive, robust regression, polynomial regression, bias-variance tradeoff. Okay, that's the agenda. It's quite extensive. We might have to dig deeper into maths, the APIs, okay, a lot of concepts around it. Let's get started. To begin with, let's first understand what are linear models. In terms of classification, say you have data like this. This is one class. This is another class. Okay. And when you say this data, class A and class B, this is class A and this is class B, right? When you say the data class A and class B are linearly separable, what you mean by that is you can draw a line or a plane. Okay, plane is nothing but more dimension of line, right? A line or a plane which can separate class A from class B. That's what you call linearly separable data. There are some data which is not linearly separable. Like this. So you cannot draw a line to separate this X from O, right? There is no, so this is what your linear models cannot achieve. Okay, linear models like we have linear regression, logistic regression. Okay, this is what those linear models cannot achieve. You might have to rely on nearest neighbors, decision tree, or others for that. Okay, this is in terms of classification. Now let's see in terms of regression. Okay, this is price. This is size for house. This is house size in square foot. This is price of the house. And say you are plotting. This is the data that you have. Okay, and okay, all you can do is you can predict a line which represents the relationship between square footage and price. Okay, so then you can say there is a linear relationship between square footage and price. So there is a linear model which exists between them. Of course, this is number of features is only one in this case. If you increase the number of features rather than line, it will be a plane. But as long as it is a line or a plane, you can say that is a linear model exists between them. Okay, that's what linear model means, and you can have linear model for regression and classification, and that's what we'll discuss throughout this module. The first of them is to understand simple linear regression. Let's see. This is the same data. This is your square footage. This is your price of house, right? And here, so this is for different values of square footage, and this is for different values of price. Okay, say 1,000, 10,000, 500 square feet, 200 square feet, 17. I mean, it's in order, right? So you are plotting this. What it means is, right, number of features in this case is 1. Okay, and target is 1. And we need to find a relationship between feature and target. Okay, and in this case, we are trying to predict a line. So what is the formula or equation of line? Y is equal to W0 plus W1x, right? So this is the equation of a line. Given value of W0 will be intercept. So assume that, this is the line. So this will be your W0 and slope is your W1, right? So what we have here is, so this is the line. So all we need to find is the best line which represents the relationship between square footage and price, right? That's the objective here. We want to find the best line which represents the relationship. Now we need to define what is best line and all that. We'll come to that. But this is when you have one feature and one target. Of course, if you increase the number of features, okay, like in this case, if you have P features, okay, or you say P independent variables and one dependent variable, right? P independent variables or P predictors, right? So this is your features, x1 to xp. These are your features, and these weights are coefficients. Okay, so if you think this particular xp feature is more important compared to x1 feature, assuming that x1 and xp are in the same scale, right? Like if we're talking about weight, both of them are in kilograms, right? Okay, so we'll discuss about scaling part in pre-processing chapter, but if assuming that both of them are in the same scale, this if w1 is higher than wp, then we can say that, you know, x1 is more important than xp. Okay, this is the interpretation part of linear models. But what you're trying to do here, we are trying to predict the target based on the relationship between feature data and the coefficient. And you can see some value here, which is feature independent, W0, the intercept part here, which is feature independent. Okay, so all you have to do is, given the number of features, you have to predict the equation like this, which represents the relationship between feature data and the target. Now, for different values of W0 is your intercept and W1, we have a different line, right? For different values of W0, W1, you have different line. The objective here is, suppose you have data like this. This is one possible line. Of course, you have a line like this, you have a line like this. So there are infinite possibilities, isn't it? Okay. What you have to do is you have to find the best line. Okay, and we have to define now the best line. The best line is the one for which the RSS, right, residual sum of squares is least, or the error is least. Now we need to define what is this residual sum of squares. For example, take this is hypothetically assume the line, okay, that we want to validate for, and this is all our data. So this is the predicted price, isn't it? And this is the actual price. Okay, so what we have to do, this is the predicted price y cap. Okay, and since this is a straight line, W0 plus W1x, and y is your actual price. So predicted price minus actual price for all the data I is equal to 0 to m, considering you have m points, you are summing the square of difference between the actual price and the predicted price. Okay, so this is what you say is sum of square error. This is the error, RSS. What you have to do is you have to find the line which has the least error. That's the objective. Okay, among all the possibilities. So this is what is your minimization function. Okay, this is what you have to minimize. Okay, for this we have gradient descent. Now let's understand how does gradient descent works. Okay, let's start with gradient descent. Okay, so linear regression uses gradient descent to minimize RSS. Okay, so that's what gradient descent is. It actually finds the best. So this is the cost, okay, or your RSS. Okay, and for it, here we see in the diagram theta 0, theta 1, you can assume this to be W0, W1. Okay, thetas are also representation of weights. Okay, so this is the cost or the RSS for this pair of W0, W1, right? And this is different values of theta W0, W1, and this is different value of W0, right? For different combination, this is the cost, and this is what you're plotting. So what is the best weights for which the linear regression should best weights for which the linear regression should have the least RSS? It's basically this some lowest point of this contour, right? Probably a point like this. Okay, so that's what we have. Gradient descent have to calculate. Let's understand now how does gradient descent really work. Okay. Now for the simplicity of math here, we have done some assumptions so that we can understand the algorithm. Okay. So let's say this YP is our target or the prediction. Okay. A is the intercept and B is the coefficient. Okay. And this is the target to be, this is a prediction. Okay. And Y is your actual. So A is the intercept, B is the coefficient. Okay. Okay. And to simplify your RSS calculation, it's pretty much, we have just added 1/2 here so that it nullifies all the 2 and makes the math really easy. All that matters is the relative difference between them. The actuals does not matter. So sigma of I 0 to m. Okay. Then yp minus y square. That's your RSS. Okay. So to begin with, we have a data like this. Just show. Okay, we have a data like this. Is the house size, is the house price. The reference for this is for this table is mentioned in the notebook. To begin with, what gradient descent do is assigns random values. Okay, there are of course different techniques to assign random values, but that's what gradient descent does. It assigns random values. So okay. Followed by that, we need to find how much. Okay, what is the relationship between A and the loss, B and the loss, and try to change the value of A and B in the reverse direction so that we can reduce the loss, because that's the objective. Your objective is to reduce the loss, and we want to find how A is related to the loss so that we can change A and we can see the loss getting reduced. How is B related to loss, and then we can change B and we see the loss getting reduced. Okay, so to do so, what you have to do, you have to find G by GA of this RSS, right? That's what we have to do. So we have done the math here, the calculation here. So let's understand it. Okay, we want to find relationship gradient for A to loss. So this is what boils down to 1/2. This to simplify y minus yp, and it is for all the data. Okay, so expanding yp, as we have seen earlier, yp is equal to a plus bx, right? We are expanding it over here, and then we are just expanding the square. So a square plus b square, and you have a minus 2ab, right? Then expanding this, a square plus bx square plus 2abx, right? This is an expansion for this. Right. Okay, then 2ya, and you can see minus 2ybx. Right. Now we are doing this with respect to dou a. So we will remove all the data which does not have any a. So it will treat this as a constant. It will treat this as a constant. It will treat this as a constant. Okay, so all we are left with a square, abx, ya, all the elements that have a in it, right? All the others will be constant. So on doing dou by dou a of all this, a square by power builder rule, it will be 2a, 2abx will be 2bx, right? Minus 2ya will be minus 2y, right? Then we can see here this 2 factor adding, and that was the reason why we added 2 over here. Okay, just to simplify this is taken off, a plus bx minus y. And remember, what is a plus bx? It is yp. So we have this yp over here, yp minus y. So to put it in simple words, dou by dou a of RSS is equal to yp minus y. Now let's see it with respect to B. Okay, so loss. So again, expanding, you have a plus bx, then you expanded this a plus bx. So you're removing all the data which does not have b in it. So this all got removed. So all that remained was this, and this guy. On doing dou by dou b of this, 2bx square, right, by power rule, 2ax, 2yx, right? That was all. Getting rid of 2 part. So this and we took x out, a plus bx minus y. So again, a plus bx is yp. So that leads to, so your dou by dou b of loss is equal to x into yp minus y. Okay, so now that's what we see here. Now let's understand the whole thing and the entire process using this housing data. We have, this is the data, and when I was talking about it earlier, the interpretation part, we need to bring every data to same scale. Okay, that's what we did. Min max scalar here. Min max scalar means it will subtract the minimum value from the column, from each column, and divide it by standard deviation of the data. And that's what we do here. See, xx subtracting by minimum value. And so let's see here. So we have this housing data. This is the house size, is the house price, and we want to bring data to same scale. That is why we are doing min max scalar. Okay. So for doing min max scalar, you are subtracting minimum value of this column from this. That is why we see x minus x min, and then same we do for this column, and we are dividing by the max value and min value. This is your min max scalar. So we get this results. This as a result here. Okay. Now this is your new value of x and y. Now we need to calculate the prediction. So let's have our initial value. This is the initial value of a, 0.45. Of course, it can be anything. This is the initial value of b, and total number of data is of course 10 in this case. So your yp is a plus b xs. So this is the first value that you're taking. So let's test with right. Let's test with this value. Okay, second row. So what we have is a plus bx. So 0.45, that's the value of a. This is your intercept, and 0.75 is your b, and your current value of x is 0.22. You can see here. So what this yields is, this is your prediction, 0.62. Right, this is the prediction. What is the actual value of y? Okay, in this case it is 0.22. Right, after transformation, this is the actual value of y. So now you see the loss will be the difference between them, right? Predicted value minus actual value. Okay, that's your SSE for this particular guy. Predicted value minus actual value, and you're doing a square of it. So of course it comes to 0.4, and 0.4 square is 0.16. That is the value that you see here. Okay, so for each of these we calculate the SSE here. Okay, for each of these, and what is your RSS? Okay, sum of all these things. That is what boils down to 1.3473, right? Sum of all this. Now let's see, let's proceed further. Okay. And above we have calculated our G loss, right? That's what we have calculated of loss, right? Losses per mean squared error. So MSC, we have written it below. It is nothing but yp minus y, right? So your value, this value, right? Your this value is actually by a. This is the prediction, and this is the prediction. This should be here. Okay, this is yp minus y. So what is the value of yp as of now? Okay, yp is your 0.62 and y is your 0.22. So the gradient is 0.04, right? So now we're seeing with respect to b. Okay, so you have yp minus y into x, right? So so this is the value that we have here, 0.4, and yp minus y is 0.4 into current value of x is 0.22, 0.2, and that is what yields to 0.88. Okay, so that's how the values of these are calculated. Now we need to see our new weights, right? New coefficients which need to alter. We need to check that out. Okay, so assume that we have this as a learning rate. Now, in this diagram, okay, you travel, so assume that you start searching from here, right? You need to find the lowest point. You have a jump size here. Okay, you test this, you test this, this is a jump size, or this is also known as alpha, learning rate. So your new A will be, okay, previous A minus learning rate into the gradient of A. After you calculated gradient A, your new value of B will be B minus alpha gradient of B. Okay, so let's see here. So we have, this is your default first value of alpha, and you have 0.01. We have this is the default learning rate we have configured, and the gradient that you have calculated is 3.3. Now let's see how that is calculated. Okay, so that is nothing but sum of, for you did this entire drill for all the data, and the sum that comes out is 3.3, right? And that is what we are using here, right? That is what we are using at 3.3, and the new value of A is 0.42. So you repeat the entire above process with 0.42 of A and 0.73 of B, right? So that's how the new value of A and B are calculated. So this is a minimization problem. You continue doing this exercise till you find your loss being not improving on changing the value of A and B, right? That's the whole point here. So this is how your gradient descent works. Okay. In other, to put it in simple words, okay, say this is your curve for your loss or your mean squared error, right? And this is some value of theta, right? All you might start from here or here. All you intend to do is find the point at which of theta 1 at which the mean squared value is least. So that's why it is trying to find the relationship between the mean squared error and theta 1, and based on the relationship, either it will move left or move right wherever it currently exists, right? That's the point. That is your this is what gradient descent algorithm really do. You can implement in not NumPy also the entire process, and see how linear regression is actually internally implemented. Let's proceed further. Okay, and try to understand how does scikit-learn actually provide this API to do the entire stuff. Okay, so we have this make regression API in sklearn datasets, which is rich of libraries. Okay, and let's see how does it generate the data. So we are generating the data here, make regression data, number of features 1, that is only one feature, and the noise is 10. That is why we see the distribution over here. Number of samples is 1000. On plotting this, we see a data generated like this. So of course we are expecting a line which is something like this, right? Okay, and scikit-learn provides you the entire gradient descent hidden inside this linear regression API. Okay, so this is what we are doing here. We are creating a empty instance or an unlearned instance of linear regression. This is the instance creation. We yet need to train it. So this has a couple of hyperparameters which basically tells you how will this be configured. One of them is fit intercept, which tells whether the model will have if you make fit intercept is equal to true, the model will try not to have an intercept. That means in case this line will always pass through the origin, it will make W0 as 0. Okay, by default it is set to true. That's mostly fine. And you need to normalize whatever data you're feeding to the model. If you manually or yourself normalizes, that's fine. If you're not normalizing it, you can set this normalizes into true. It will bring the data to the same scale. Okay, this is required in terms of interpretation of model, which I'll talk about it later. Okay, so normalize is equal to true will normalize the data. Otherwise, you might have to normalize yourself. Okay, so these are the two important hyperparameters. And what it returns as a result is one is coefficient, which is the weight for each feature. Okay, and intercept, which is like feature independent information, which impacts the model accuracy, right? Okay, and you have two popular functions, fit and predict. Fit will train the model, it will internally execute the gradient descent, find the best value of coefficients and intercept. Okay, predict, after the calculation of coefficients and intercept predict will for unknown value of target for a feature data, it will predict target. Okay. Also, linear regression, like many other algorithms, are capable of handling multiple targets. Okay, what does that mean is, as of now, we have seen target of only one dimension, target can be of two dimension, right? It can have multiple columns. Okay, and if for say that you have this feature data, okay, and this is feature data, and you have this target data. So you can see three target data and 5 feature data. So there will of course be a relationship existing between the target data and what linear regression allows you to find multiple targets for same feature, so that the relationship between the data is maintained. If the target is very much independent from each other, you can create 3 different models to predict 3 different values, or you can do that in one shot. So computationally fast, since you are doing that in one shot. Model is optimized for multiple target. Model do not use the relation. Okay, so here it maintains the relationship between them. Okay, so and linear regression is capable of dealing with multiple target. Multiple target means you have as of now dealt with target like only house price. Also you can have things like based on other parameters. You're predicting house price, you're predicting age of house, right? You have multiple targets over here. So the benefit is single model can predict multiple targets. Of course, you can use 2 different models to predict 2 different targets, but that is computationally expensive. The model is less interpretable, okay, and you know, they do not use a relationship between the target, which this guy does. Okay, let's now get into training the model. So this is the empty model, like empty brain. You're calling fit function to train the model x and y. This is your and few things to take care of. The in fit function, y can be 1 dimension and 2 dimension both. X should always be 2 dimension. That means it should be rows of columns and information. Even if it is 1 column, you need to change it into rows of column. Okay, so that's a prerequisite. X should be rows of columns format. And when you do LR.coefficient, it will return you. When you do LR.coefficient, it is returning you the coefficient that is learned, right? The slope. Okay, when you do intercept, it will return you the this point, the intercept point. Okay, when you make fit intercept is equal to false, the intercept will be 0, and you will get a different coefficient, which is returning the best RSS. Okay, and if you want to predict using the same model, LR.predict. Okay, you are giving the same data that you used to train the model. Okay, and it is predicting. And if you plot it, we can see this is the line that is predicted here. The orange line is the one that is predicted. Okay, you can see this line, and yellow blue line is the actual data. So of course, this is what simple linear regression. Okay, there are certain limitations around it. It is heavily impacted by outliers, so you might have to take care of outliers, or you might want to use techniques which is capable of dealing with outliers. Then you have non-linearities. Of course, this is linear model. It assumes there is a linear relationship between feature data and target data. If that does not exist, this is not the one you should be using. Too many independent variables. If you have too many features, it suffers limitations, and in that case, you will use techniques like SVM and all. Okay, but simple data, use simple problem. Always remember, don't kill a mosquito with a cannonball. Okay, if you can solve something with simple solutions, go for it first, and know that if you cannot solve it with simple solutions, then go for the advanced approaches. Okay, multi-collinearity. So the fundamental assumption that this linear regression or linear model have is there is independence among the features, okay, or the predictors or the independent variables. Okay, so multi-collinearity is when you say there is a relationship between the features. Okay, let's proceed further. Okay, let's start with regularized regression methods. So as we discussed earlier, linear regression is impacted by outliers, and the coefficients that are generated is very much impacted by the data. So we want to make sure that coefficients are not impacted heavily with the data. Okay, so that's what is regularization comes into picture. So if your data is not showing, it's deviating from regular pattern a bit. So you might see that linear regression does not work out pretty well. So you might want to test regularized techniques to handle those situations. In simple words, okay, regularized techniques will, tape down your coefficients. Assume, these are different coefficients. This is coefficient value, and this is the A, B, C coefficients. So by default, your coefficients can be like this with linear regression. With regularized method, you will reduce the peaks of the coefficients. Let's see with an example. So the first one is ridge. So ridge, and this alpha controls the peakness. Okay, if alpha is equal to 0, you say that there is no taping happening. So let's say this is the data, this is the target, right? You can see a 2-dimension data, and this is the target here. When you fit, and you're fitting this with ridge regression and logistic regression both. Correction, you're fitting this with ridge regression and linear regression both. And the coefficients that we see, which is generated on ridge, is 0.44 and 0.4, pretty much low values. And if you see, okay, the coefficients that are generated in LR, in linear regression, it's pretty high. You can see 10 to the 14 and 10 to the 14. So yes, it is heavily impacted by these values, right? Okay, maybe the data is too less and it will converge in further, but what we see important thing is ridge regression, is not heavily impacted by each data. It understand more of a general trend. Okay, let's now add some outliers in the above data, okay, which we used in our previous example, this data. Let's add some outliers over here. Okay, so now the data became like this. This is the most of the data, and this is some of the data. We just added some outliers over here. Now we want to see what is the impact of linear regression and ridge regression on it. And if you're using a linear regression, okay, we are training the linear model, okay, getting the output, and we are training the ridge regression and getting the output. Okay, so you can, let's see here. So this is the actual data blue. The black one is prediction without outlier. So you can see it is pretty good. And because of these outlier, prediction has come here, right? And if we do this for linear regression, so this red one is linear regression and black one is ridge regression. So since this is only 2-dimension, so that is why we see it like this. But you can see this ridge regression is lesser impacted than your linear regression. The linear regression completely just moved here. The ridge regression, most of the part it is here, some part it has moved here. So ridge regression is lesser impacted by outliers. Okay, and ridge regression takes a parameter alpha, and let's see what happens. What we have done here is we have generated different values of alpha. We can see 10 raised to the power minus 6 to 13 raised to the power minus 5, right? So you have different alphas over here. Okay, this is the first 20 alpha. So you have, okay, so you have alpha to 10 raised to the power 6, 10 raised to the power minus 6 to 10 raised to the power plus 6. So that's the range of alphas to here. Alphas is the one which decides how much taping it will do. Okay, and let's now see the impact. So on this, on the data that we have generated. Okay, so now when alpha is equal to 0, okay, we will see that ridge regression behaves very similar to your linear regression, where alpha increases, okay, and this is the diagram which best explains this. So this is when alpha is very less, and this is when alpha is very high. When alpha is close to 0, this is where your, so this is alpha is very less, right? And as alpha increases, the variation between the coefficients reduces, and if you further increase alpha, it is making those coefficients in the same values, in the same range, right? So this is what alpha does. Alpha tapes it reduces the impact. So we can see these are like different values of coefficients, right, with different colors, different values of coefficients. And as we keep on increasing the value of alpha, you can see the coefficient is coming closer to 0. And finally, all of them stabilizes on further increasing the value of alpha. Okay, so that's the fundamental takeaway from ridge regression. Okay. Now we have Lasso. Lasso is pretty good in terms of reducing the number of features, and it predicts sparse coefficients. Say if you have features like this, you can see here you have two columns and all the values of all these columns are same, right? So what will this guy do? This guy will figure out the minimum representation of the data and find coefficient for only that column. So what it has done is it has realized that these two columns are same and the second column is not much of an importance, so it has made the coefficient 0 and the first guy is 0.5. Okay, so this is a good technique to reduce the feature spaces. And the next technique is ElasticNet. So what it does is, rather than actually removing the features which it thinks as is not required, it gives it reduces the weightage of both of them. So this is what it does. So in situations where you do not want to get rid of features, even if they are correlated to each other, you can use ElasticNet to have them with reduced importance, so that the collective importance makes sense. So this is very useful when the data shows multicollinearity. So as of now, all of these, what we have seen so far is taking care of your regression. Okay, let's now get into classification using logistic regression. So as of now, we have seen linear model for regression. Now let's see linear model for classification. So we have data like this, right? This is one class and another class. We want to predict a linear model or a straight line which divides the data. Okay, so if you predict a straight line, right, the output would be something like this, right? The value of y that will be predicted will not be 0 or 1, or you cannot say this is class 1, class 2, right? You cannot do that. So that is where the output of this line given a value of x is subjected to sigmoid function. Okay, sigmoid function. Sigmoid function takes this value and converts this in the scale of 0 and 1. And this is how your sigmoid function is represented. Whatever is the outcome, okay. So this is 1, this is 0, okay, and this is a value of this is a value of x. No matter what is the value of x, you would find out. Okay, you will convert that in the scale of 0 and 1. Okay, so that's what it does here. Okay, all you will put is the value of x, it will predict y, and then y will be subject to sigmoid, which will convert the value into 0 of 1. So if you say if it is a bi-class classification, if the data is between 0 and 0. Less than 0.5, you say this is class A, and then 0. Greater than 0.5 and less than 1 less than equal to 1, this is class B, right? So this is how it is calculated. So let's now understand this using the data. So we again have make blobs. This is the scikit-learn library for generating the data. Okay, and using make blobs, we are generating data, and this is like 2 blobs of data. And okay, the standard deviation of the cluster is 2. This is the 2 centers. This is the data that you have generated. Okay, now this is a very useful technique which we'll use throughout the course. This is generating for this data, right? It is generating all the data in this range so that we can understand the decision boundary. So you can see here, this is x, this is y, and later on when you are creating the model, okay, we will be combining them both. Let's understand. So this is like generating all the data, okay, so that we understand the decision boundary. This is the model we are creating, and see, we are training the model x and y, the actual data. Okay, then we will predict for the data generated xx variable. That means it will bring that in 1 dimension. This is 1 dimension, and it's concatenating it. Okay, so it is generating all the data in this particular range in max value. It's generating all the data, and then it is predicting for this, and that's why we can see the decision boundary. This any data which comes inside this decision boundary will belong to this class. Inside this decision boundary will belong to this class. So this is the line which is being predicted over here using this logistic regression. Of course, this is 1 dimension. This data has 2 dimension. You can increase the number of dimension. The plane will be having 1 lesser dimension to that, like the 2 dimension here. So the separator will be 1 dimension. If there is 5 dimension here, the plane will be 4 dimension. Okay, so that's all for logistic regression. Let's proceed further. Now, all of the models that you have seen so far, the linear regression, the logistic regression, is not capable of online learning. Now, what is online learning is you train the model, you get some new data, you train the model with the differential data. This is what the previous models are not capable of, but this is what is required in real-time applications, right? Because you'll continuously get data from your data pipeline. To handle the situation, we have online learning models. So there are two breeds of it: stochastic gradient descent and passive aggressive algorithms. Okay, two breed of it. And what basically these guys do is, this guys has the ability to learn on differential data, and we can see the model improving. So this is just a small example to show how it behaves. So we are generating some data here, make classification, right? Of course, this SGD classifier and passive aggressive, both of them can do your regression and classification both. Okay, and this is very useful when the data is in the scale of 10 to the power 5 rows or more. Okay, below that your basic algorithms is fine. Okay, and we are using this classifier. Okay, and first time you're training, you don't use the regular fit function, you use partial fit. Partial fit, training data, target data, and then classes you have to pass. This is the classes that you have over here. So first time you're doing the prediction with the test data, your accuracy is 79. You train it further with next 1500 rows of data, your accuracy improves. So right, so you can see the online thing getting impacted. We'll have a separate module for out of code learning where we'll be doing projects using this, but to understand there are linear models for online learning. So stochastic gradient descent, passive aggressive. We'll be not getting into details of this algorithm at this point of time, but is subject of later modules. As we have seen, this linear model is heavily impacted by outliers, and let's not deny the fact that real data is full of outliers. Okay, so we have few techniques like ransack, Thalson, and Huber regressor, which is much robust when outlier data has to be considered. Okay, so just to put it in a nutshell, ransack is better algorithm than rest of the stuff, works mostly good in all the situation. Let's see what really it brings to the table. Okay, so among all of those, let's see ransack. We are generating the data, adding some outliers. We are generating regular linear regression line with that, and we are using ransack regressor for that. We want to see comparison between. So this is the data. This is the data. This is the outliers that is present here. We want to see from the prediction. This is the prediction for ransack. This is the prediction for linear model. We want to see where are they generating the line. We can see here. The orange line is for ransack. So even if there are outliers, it is hardly impacted. Very good behavior. Whereas the linear regression, you can see the complete trend has been changed. So you can understand, you have to see if the data consists of outliers, and if you're aware of that, better use ransack. So it works pretty well. Okay, let's get to the next module. Okay, let's get into polynomial regression. So as of now, we have seen a line or a plane getting predicted, but we can actually achieve kind of nonlinear separators in using polynomial regression. Let's see what it means. Okay, so here you can see there are two classes of data. There is this purple color class of one data, and this is this orange. Of course, we understand that we cannot have a line which acts as a predictor, acts as a separator between this. But of course, we can have a circle, isn't it? Okay, we can have a circle which represents, which separates both of these classes. So if we can convert this data into, like we have this x and y, and if you're translating this into x square and y square, then definitely we can predict for equation of a circle, right? If you are predicting the coefficient for this, we are predicting the equation of a circle which separates these two classes. So this is the big circle is the way to generate this data. By default, there will be two classes, 1000 samples, noise is 0.4, that is where the distribution. And initially I'm trying to plot it. Now to convert, we have data of x and y. We need to convert this to the higher scale. That is what your polynomial features does. Okay, this is the transformation technique. Okay, polynomial features. You can study this in a module, pre-processing module. Okay, so what this will do is, we mentioned degree 2, given a particular data with x and y, it will translate that into x raised to the power 0. That means first column will be 1, next column will be x, y, x square, y square and xy, right? So this will be the number of columns: 1, 2, 3, 4, 5, 6. So given, and it will call this fit transform function, okay, to convert the data into higher dimension, right? So data will be now of, rather than 2 column, it will be of 6 column, right? Now we want to use logistic regression. So what is logistic regression? It will basically find the coefficients which such that, you know, the it minimizes the errors, right? Okay, so that's what it will do here. Okay, so we need to find, I mean, in this case, we can see that a 2 degree is enough. So in some situation, we might not be able to. So for that, we have to try heuristically 2 degree, 3 degree, which is giving us best validation equation. And in this process, let's you know, dig deeper into this API train test split. So what are we doing here? We are actually splitting the data into 2 parts: training data and testing data, right? You want to train the model with one chunk of data, and based, if the data is, if the model that is trained is good, it will work very well with the target data, right? So in this case, we are training the model with the trained data only. Target data, the tests, the test text and test y not used, but used in the score part, right? This is how you are validating the model. So if you can see here, 98.4 is pretty good, right? Because it is able to predict almost a circle, which will act as a good predictor, right? Okay, you can see here there are different VKs, and okay, these are your different 6 columns, right? 1, 2, 3, 4, 5, 6, right? These are values for each of the columns. Okay, so with, sometimes you, as I was mentioning, you might not be sure which is the best degree, so you might have to try with degree 2, degree 3, degree 4, and split the data into 2 parts. Training data, you should train each of the model, and using test data, you should validate each of the model. Which of the model is giving you good results for validation data will be your answer. Now let's get into get more into bias and variance parts. Okay, so this is very important to understand how those models really work. Okay, bias means these are simple models. Okay, that means it might not learn complex models from the data. Okay, fitting the data. So if you are using simple model, like if your data is circular model like above, right, or if data is little complex, but you're learning a simple model from that, what will happen during the training also, you'll get some error, training error. From testing, you'll get some error, test error or the validation error. It will not be different much. So this is the situation of underfitting as well. If you use simple models, you will find the model working good in no matter what use of data, but there will not be much difference between training error and validation error, right? What is training error? When you are, in this case, what we are doing here, this is your validation error, right? You're testing with this. So if I do lr.score train x train y, that will be a train error. Okay, a good model is one where the train error does not vary much with validation error. Okay, okay, and if the error for both of them are less, the chances of this that the model is underfit. Okay, so this is the model complexity. So if you increase the model complexity, what will happen is your training. So this is what you see here. This is the error. If you increase the model complexity, your training error and your validation error, the difference between them might increase, and right. So that is what this is your training error. This is your validation error. The bias variance was. Okay, let's now get into the bias variance part of the module. Let's understand this one thing. If you are predicting a simple model from data which is not so simple, okay, what you might be getting into the situation where your training error and testing error are not much different, but at the same time, both of them might not be good. Okay, so this is the situation of underfitting. You're predicting a simple model, okay, but both of them are not. Okay, let's get into bias variance module of this. Okay, say you have data like this, the orange points. If you are predicting a simple model, right, we can see here this blue line is a simple model that is predicted. So no matter what is your data, it might work same, right, when you're training the model and when you're validating the model, because it's kind of underfit situation. And say you have this data, and if you are touching all the points, right, what would happen is for these training data, it is fine. For unknown data, the error would be high. So there will be difference between the training error and the validation error, and which will be higher. In case of this, the difference between the training error and the testing error will not be so high, but the accuracy won't be too good either. Okay, so this is a high bias model and low variance, because the variation between the training error and the validation error will be less in this case. Okay, whereas the here high variance, that means the difference between the training error and the validation error would be higher in this case. So this is what happens when you go from simple model to very complex model. In simple model, the error difference would be less, but the accuracy would be less also. But as you keep on adding complexity to the model, the difference between them would increase. So your objective would be to have something in middle of it, like this, which has medium bias and medium variance. So this is the model that should be accepted, not this and not this. Okay, that's all about bias and variance. Okay, thank you. See you in the next module.